This problem is the conical tank problem, and it's a very common problem that you'll see in calculus. Here's how it goes. You've got an open right circular tank with this vertex down. Now we'll draw a picture here in a minute, but it has a height of 12 meters and a radius of 8 meters. Let's draw this first before we go on. So I've got this circular tank, and it's a right circular tank, which means that if I go from the center down to the vertex and over to the radius, this is going to be a right angle, right? It's not a cone that looks like this, but rather straight, vertical. Now let's finish the problem here. It says this: water begins to flow into the tank. So just imagine up here that water starts to flow into the tank at the rate, oh, there's that word rate. So what do we think? We think derivative. So water flows into this tank at 3 cubic, all right, there's a volume. So water is flowing into the tank at 3 cubic meters per minute. So every minute, 3 more cubic meters of water go into the tank. Now what else? At what rate is the depth of the water in the tank changing when the height is already 4 meters? Okay, so let's see what we have here. We're going to have water flowing into this tank at 3 meters per minute, and the height, all right, as water flows into the tank, right, the height changes. So when the height is here at 4, how fast is that height changing? Now you can imagine this. If the height is down here and you put in 3 cubic meters, we're going to get a pretty substantial change. But if the height is up here, the water's already up here, if you put in 3 cubic meters, oh, we're going to get kind of a small change in the height. So let's make some labels here. What do we know? Well, we know for sure that the height of the tank is 12, and that's constant. That is not going to change. The height is 12, so I'm going to label that with a 12. Right? The height is 12 meters. Now, I also know that the radius of that base is 8 meters. So the radius of the base, this is not changing, right? That is the structure of this conical tank. So I'm going to label that with an 8. Now, it's 12 meters and 8 meters. Now, there's 2 things that are changing in this tank. And one is the water level, right? The water level, right, as you pour water in here, the water level is going up. So the height of the water is going up. And as the height of the water goes up, that radius where it comes out and hits the side of the tank, that's going to change too. So we've got 2 variable quantities. We've got the height of the water in the tank and the radius of the water in the tank. So let's label those. Now to do that, I think what I'm going to do is I'm going to add to this drawing a little bit here. Here's what we have. I'm just going to draw that part of the tank. So as the water level is up here, say it's a level H, we're going to get this radius R. And you can see that as the height of the water, as water comes in, the height changes, and so does the radius change. So let's write what we're looking for and what we have. So what I want to do is I want to find, let's get it to right here. What I want to do is I want to find what? It says this. At what rate is the depth, H, of the water changing at when H is equal to 4? All right, so what rate, that's a derivative, is the depth of the water changing. So what I want to find here is the rate of change of the height with respect to t. So find dH dt when, all right, that's what I want to find. And then what do I know? I know that the water is coming in at the rate of, what does it say up here? At the rate of 3 cubic meters per minute. So find dH dt when dV dt equals 3 cubic meters per minute. Now, why do I know that that's a V? Well, what's happening? You're putting in a volume of water, all right? So it's a rate, so I know it's a derivative. So I'm going to put a V here. Now I know it's a derivative with respect to time because look what we have. The bottom number here is a minute. Now that's time, so that goes on the bottom. And what do you have on the top? You have a cubic, right? Meters cubed. Now that's a volume, so I'm going to put a V on the top. All right, and this is coming in at 3 cubic meters per minute. So what I want to do so far is I want to find how the depth of the water, H, is changing when we're given these conditions. The volume is increasing at the rate of 3 cubic feet per minute, and I want to find it when H is equal to 4 meters. Now we need to get a relationship. This one we're going to have to work a little bit, and I need to know something about similar triangles. So here's what we have. I'll draw this picture up here. In case you don't know it, you will in about a minute. So you have this triangle here. This triangle is going to be similar to any triangle that I draw in here. So let me draw this here. So we're going to have this, that this triangle here, okay, that's going to be this one here. I'm just drawing it outside. So this is going to be the 12, and this is going to be the 8. That is going to be similar to any triangle that I put inside here. And that's going to be the H and the R. So that's going to be similar. All right, this is similar to this triangle. H and R. Now I've got a picture, and the picture is going to help make that equation accessible. Now I need to know something about similar triangles, and what we know is this, that corresponding sides are proportional. So this side as to this side is proportional to this side as to that side. So let's write this. What I'm going to have is this, that long vertical side is to the short vertical side as equals the long base is to the other base. So we're going to have 8 is to R. So this vertical is to that vertical as this horizontal is to that horizontal. There's our equation. Now, let's see if we can solve this for either H or R. Well, I can solve it for either one, right? Here's what I'm going to get if I do this cross multiply thing, right? What I'm going to get is 12R is equal to 8H. Now, I can solve for R, or I can solve for H. If I solve for R, I get this. Let's divide by 12, right? Solve it for R, we'll divide by 12. So I will get R is equal to 8H over 12, or that R is equal to, we can reduce 4 divides into each one. So how about 2H over 3, right? So R is equal to 2/3 of the height. Or, right? Or I could divide by 8 and get this for H. So I could say that 12R divided by 8, that's equal to H, or that H is equal to, now 4 divides these, so it's 3 over 2 R. All right, so I've got these two equations now. So how do I know which one to use? Do I want to use this left equation here, R equals, or do I want to use the right equation, H equals? To help us make this determination, look back to what we're trying to find and what we're given. We're trying to find dH dt when dV dt equals 3. Now V, that's a volume. So it would be very helpful if we had a volume function. Now, this is a cone. It's a right circular cone, and there happens to be a formula for the volume of a cone, a right circular cone, and it's this. The volume of a cone is equal to 1/3 pi r squared h. Now look what we've got here. I've got a v, and if I differentiate it, I'm going to have that dv dt. And look what else we have here. We have the r, and we have the h. Now I've got the r down here, and I've got the h over here. So which one do I want to use? So looking back into the information that we have, what I'm trying to find is this over here at the bottom left. I want to find dh dt. So I think I want to have h's. So because I'm going to differentiate v, getting dv dt, and then I want h's over here because I want dh dt. That means I should get rid of the r, all right? So the plan now is to do this. We are going to eliminate r, all right? So eliminate r, all right? So I'm going to come down here, and I'm going to say, okay, r is equal to 2h over 3. So let's put the 2h over 3 in for r, all right? So I know now that since r is equal to 2h over 3, let's put that in right here. So we're going to have v is equal to 1/3 pi, and then 2h over 3 squared h. Let's keep going. V is equal to 1/3 pi. Now let's square 2h over 3. We'll get 4h squared over 9 times h. This will give us that v is equal to, now what are we going to get here? I'll get 1 times pi times 4. That's 4. So I'll have 4 pi, and then I'll have the, what do we have? H squared times h, right? H squared times h is at h cubed. So I'll have an h cubed up here, and then the bottom, we're going to have the 3 times the 9, giving us a 27. Okay, now I'm just going to rewrite this a little bit here. I'm going to send that h cubed out. So I'm going to have 4 pi over 27 h cubed. So there's my relationship that I'm looking for. It took us a while to get there, but I've got the volume is equal to 4 pi over 27 h cubed. Now we're going to differentiate with respect to time. Now if we differentiate with respect to time, I'll do it right up here. I'm going to do it over here. So I'll get dv dt. Right now the volume changes with respect to time, and the height over here, the depth or the height, changes with respect to time. So look what we're going to have here. Here's a constant, so we can write that. We will get 4 pi over 27 times, now let's differentiate. This is going to be implicit differentiation, right? We're going to have the derivative of the outside, so I'll bring the 3 down as a multiplier, decrease it by 1. So I'll have 3h squared, but then the derivative of the inside, differentiate the h with respect to t, we'll get dh dt. dh dt. Now let's just get rid of some of this stuff over here so we have some room. Okay, and we can work with this function right here now. Let's simplify a little bit. I can see that this 3 and the 27, I can reduce that. 3 will go into 3 once, into 27 9 times. So here's what we're going to have now. We will have that dv dt is equal to 4 times pi times 1 is going to be 4 pi all over 9, and then I have the h squared dh dt. Okay, let's substitute. dv dt, that's known, right? dv dt is 3 cubic meters per minute. Now I am going to use the unit, so I'm going to get 3 cubic meters per minute. This is equal to 4 pi over 9 times h. Now what is h? Let's come back over here. H is, we're finding the rate at which h changes when h is at 4 meters. So I'm going to put 4 meters in for h. So this is going to be, now I'm going to write it like this, 4 meters squared times dh dt. And of course we don't have a value for dh dt because that is what we're trying to find. So let's compute here. We are going to get, I'll do it right up here on the right here, we're going to get 3 cubic meters per minute. That's equal to 4 pi over 9 times 16 square meters, right? Square the 4, square the m, and dh dt. So now we can simplify right here, right? The 4 times the 16. So we're going to get 3 cubic meters per minute. This is equal to now 4 times 16. 4 times 16 is 64 pi, but we have meters squared over 9 times dh dt. We are trying to solve for dh dt. So why don't we just divide by this quantity right here? So it's going to look like this. I'll show this step. We're going to get 3 cubic meters per minute divided by 64 pi square meters over 9. That's equal to dh dt. Now, I'm doing a division here, right? We know how to divide. I'm going to invert and multiply, or multiply by the reciprocal. I'll start a new page here. This is getting a little tight. So I'm going to have this. I'm going to have 3 cubic meters per minute times, all right, let's invert it. We'll get 9 over 64 pi square meters. That's our dh dt. And maybe we can simplify this a little bit. Let's see. What we can do here is we are going to get 3 times 9 is 27, right? So I'm going to have 27. But look at these m's. I got 3 m's up here, right? M cubed, and I got m squared down here. So these 2 m's will cancel with 2 out of those 3. So this one will cancel with 2 of those, leaving an m. So here's where we are. I'm going to have 3 times the 9. 3 times the 9 is 27. I'll get an m left. And then this is over what? 64 pi minutes per minute. That's dh dt. But I'm going to write it in a little bit better form. How about this? I'm going to get 27 over 64 pi meters per minute, right? I'll just break off the constant and have the units out there at the right. Okay, now, does everything look reasonable? This is dh dt. This is equal to dh dt. Now, this does look reasonable because we have the height, right? The height is on top, and the height is in meters. Those match. And the bottom is t, time. And I've got minutes. So it looks reasonable. I'm going to rewrite it slightly to look like this. I'm going to say that dh dt is equal to, now I'm going to write it like this, 27 over 64 pi meters per minute. That makes it easier for me to make an interpretation. So let's interpret this. So I'm going to write an interpretation. So here's what I'm going to say, because everything starts here at the height is 4 meters. So let's say that when the height of the water in the tank is 4 meters, now let's write our changes. We'll say if the time increases, I'll abbreviate, increases by 1 minute, we expect the height of the water in the tank to increase. We'll say why we're going to increase here instead of decrease. Increase by about 27 over 64 pi meters. So our interpretation is this. When we're at 4 meters of water in the tank, if we increase by 1 minute, right, look at the bottom here. The bottom is really 1 minute. If we increase it by 1 minute, right, if the bottom increases by 1 minute, the top's going to increase by this much right here. So when the height of the water is in the tank is at 4 meters, if we go 1 more minute, then we expect the height of the water in the tank to increase by about this number right here, 27 over 64 pi meters. Now we're saying increase. How do we know it's increase? Well, look what we have. I'll just write it down here. dH dt is equal to this number right here. Now that's a positive number divided by positive number, right? So what we're looking at here is that I've got a positive divided by a positive, which is positive. So what we've got is that dH dt is positive, and positive implies, all right, the derivative is positive. That implies that that variable right there is increasing. So that implies that h is increasing.